Hello. This lecture will cover pages 6 through 11 of my lecture notes. Please print those pages out and have them in front of you as I present this lecture on capacitance and inductance, Chapter 6b, investigating how capacitors and inductors react to DC voltages and currents. Before we start on page 6, I want to take a look at the top, and I want to mention something with regard to communication media and transmission lines. We're going to take a look at an ideal transmission line. An ideal transmission line, basically, from point A to point B here, we're going to neglect a distributed resistance. It would just be a wire. And we've used, most of the time, that's what we deal with. We deal with ideal communication media or ideal wires. But I want you to recognize that at the higher frequencies, you have to take into consideration our three passive components: resistance, capacitance, inductance. From this point to this point, if it's any significant distance, measured in thousands of feet or miles, there is resistance. So if you have a pulse, we'll just use a pulse, from 0 to 5 volts, and as it travels down this line, when it gets down to this point, you're going to have an attenuation or a weakening of this signal. So we refer to that as attenuation. So notice you might have 5 volts here, but by the time you get down here, you may only have 4 volts or 3 volts. That's due to the voltage losses in the distributed resistance, and we're showing it as resistance here and resistance here and resistance here. Usually when they model that, it's so many ohms per feet. Okay, let's look more practically at the circuit in terms of not only these resistances, but you have resistance, you have inductance, and you have this parallel capacitance to ground. And then in the next foot, they model more resistance, same inductance, and same capacitance. And within the next foot, they have resistance, we have inductance, series resistance, series inductance, and parallel capacitance. Okay, so you'll not only get an attenuation in this signal at this other end due to a loss in voltage because of the resistance, you're also going to get an effect that gives you some roundness or some exponential shape to the pulse. That's due to the capacitance and the inductance in the circuit, or in this wire. So, and at the higher frequencies, that capacitance and that inductance plays a significant role. At the low frequencies, pretty much ignore it. So that's attenuation. That's true attenuation of that signal. It gets beat down in magnitude because of that resistance, the loss in voltage distributed amongst the R's, and it gets a roundness, exponential shape to it on the rising edge and on the falling edge out here. And that's because of the capacitance and the inductance that's measured in that wire. Let's investigate how capacitors and inductors react to DC voltages. Before we work the next 4 problems, you have to, hopefully you have this memorized by now. Remember, before you work these next 4 problems, you have to keep this in mind. Voltage cannot change instantaneously across the capacitor, and current cannot change instantaneously through an inductor. There are 2 rules that you will take with you through your career. Starting out on page number 7. What we're going to have here on page 7, example number 1, a simple resistive capacitive parallel circuit. All we have is a 12 volt supply here. We have a switch. This switch we're going to close at t equals 0. It's open from minus infinity to t equals 0, and at t equals 0 it closes. And we have a capacitor here of 10 microfarads, and we have a resistance of 6 ohms. And I want to know what is the voltage with respect to time across the capacitor at t equals 0 plus. In other words, you throw this switch, and at the instant above 0, t equals 0 plus, what is the voltage across that capacitor and why? Well, you know that at time t equals 0 minus, That's an open switch, so the voltage there is 0 with respect to ground here. The voltage is 0. And you know voltage can't change instantaneously across the capacitor. So when you throw that switch, the voltage here at t equals 0 plus has to equal 0 volts. What is the current to the capacitor at time t equal 0 plus? Well, voltage can't change instantaneously across the capacitor, but current sure can. That looks like a short circuit when you first throw that switch. Look back at your equations. Mathematically, it'll tell you that if you look at your equations. But I'm telling you that at time t equals 0, when you first throw that switch, that looks like a short. So if that looks like a short current, if that looks like a short circuit across that 6 ohm resistor, that current is going to be infinity amps. Why? Because that looks like a short. What is the voltage across the resistor at time t equals 0 plus? Well, it's 0 volts also. Why? There's 2 reasons for that. You can explain it 2 ways. One is because it's the same voltage across the capacitors, across the resistor, they're in parallel. That's why voltage is 0. But what's another reason? Well, there's no current flowing. When you first throw this switch at time t equals 0 plus, no current can flow through that resistor because this looks like a short. All the current flows to that capacitor. So no voltage through there, no voltage. No current flowing through the resistor, no voltage. There's 2 ways to explain that. Make sure you understand that. What is the current to the resistor at time t equals 0 plus? Answer: the current at time t equals 0 plus is equal to 0 amps. Why? Well, I just explained that when I explained this voltage. All the current goes here. It looks like a short. Let's take a look. We pretty much exhausted what happens at time t equals 0 plus. What about when you close this switch and you keep it closed for an infinite amount of time? Now I want to know, what is the current to the capacitor at time t equal infinity? Well, do you know the answer? It's equal to 0 amps. Why? Because it looks like an open circuit. Current can't flow through there, don't forget. So once this gets charged up to its 12 volts, once this gets closed and you get that charged up to 12 volts, current cannot flow through there. So you get 0 amps. The voltage across the capacitor at time t equal infinity. When you throw this switch at time t equal infinity, the 12 volts is here. 12 volts. They're in parallel. Another way of explaining that is the capacitor gets charged to 12 volts. What is the voltage across the resistor at t equal infinity? Well, it has to be 12 volts also. Exactly the way it was across the capacitor, because they're in parallel with one another up here. And what is the current to the resistor at time t equal infinity? Think about that. I give you answers here, but you're going to have to do this on your own shortly. You throw that switch, that looks like an open circuit. So you have 12 volts across that resistor. We've calculated that up here. Just divide by 6 ohms and you get 2 amps. That's all the possibilities of current and voltage in that circuit from the time the switch is open, the instant you close it, and you allow steady state conditions to settle in. That's t equal infinity. Let's look at example number 2. A little bit different. Example 2, we have a series circuit here. It's series. It's not a parallel circuit like this. You should be able to, taking this circuit, 12 volts, plus, minus. You throw that switch at t equals 0. And I want to know what is the current to the resistor and the current to the capacitor at time t equals 0 plus. Right after you throw that switch, t equals 0 plus. And what's the voltage across the capacitor at t equals 0 plus? What's the voltage to the resistor at t equals 0 plus? And then we exhausted those calculations. we look at everything at steady state whenever that switch is thrown, and it's closed for an infinite amount of time. And I want you to go through each one of these answers. If this was a face-to-face class, we would do this one at a time. I'll do a first couple of them with you here. What's the current to the resistor and the current through the resistor and the current to the capacitor at time t equals 0 plus? You just throw that switch. Well, that's going to look like a short. At time t equals 0, that's going to look like a short. So the current is 12 divided by 6. It's 2 amps. Why? Because the capacitor looks like a short circuit. What's the voltage across the capacitor at t equals 0 plus? Right after you throw the switch at t equals 0 plus. Well, you can't change voltage instantaneously across the capacitor. When that switch is open, there's 0 volts across that. And when you throw that switch, you can't change voltage instantly. It's going to stay at 0 volts. Why? Because you cannot change voltage across the capacitor instantaneously. You memorized that already. What's the voltage across the resistor at time t equals 0? The answer is the voltage across the resistor at time t equals 0 is 12 volts. Why? Because this looks like a short circuit, and all 12 volts gets dropped across that because this is a short. Remember Kirchhoff's current voltage law? The rises have to equal the drops. Now I want you to calculate the current through the resistor and the current to the capacitor at time t equals 0. Well, they're both going to be equal to 0. Why? Because that looks like an open circuit. At time t equal infinity, at time t equal infinity, when you close this switch and you keep it closed for an infinite amount of time, it looks like an open circuit. Current can't flow. You should be able to get this one, you should be able to get this one. Observation. In the steady state, when all short-term transients have settled, transients are short-term events. So, when you close the switches, when the transients are all done, and that's what these were. These are things happening in a relatively short period of time. These are transients, both here and in that previous problem. Example 1, through t equals 0, through here. Take a look at that. These are all the transients at time t equals 0 plus. Once these have settled through, capacitors look like an open circuit. Here we have an example with an inductor. Now let's do some RL circuits. I'm going to let you go through here and I'm going to let you calculate currents and voltages. I'll write a few of them down here, see if you can get them. But to do this problem, these are inductors. This is a parallel inductance and resistance. This is a series inductor and resistance. The observation is going to be here, and I'll give you the observation first. In the steady state, when all short-term events called transients have settled, inductors look like an short circuit. Not an open circuit like capacitors do. Inductors look like a short circuit. So, if you go back here, and I would write, for instance, what's the voltage across the inductor with respect to time, which has to be the same thing as the voltage across the resistor with respect to time at t equal 0 plus. I mean, when you first throw this switch, that's 0 plus. So what's the voltage going to look like across these devices? Well, current can't change instantaneously through an inductor, but voltage still can. It's not a capacitor. So the answer there is 12 volts. As soon as you throw that switch, there's 12 volts there. What's the current? And since there's 12 volts here, there's 12 volts there. These are in parallel. What's the current to the inductor, or through the inductor, at t equal 0 plus, and then y. Think about that. Should work these out and make sure they make sense to you. The current at time t equals 0 has to be equal to 0 amps. Why? Because before t equals 0, at t equals 0 minus, the current's 0. It's an open circuit. Well, when you first throw that switch at t equals 0 and t equals 0 plus, that's essentially the same period of time. Do you understand what I'm saying? T of 0 minus and 0 plus are all the same relative period of time. And current can change instantaneously through that inductor. So it's 0 amps. What's the current to the resistor with respect to time at t equals 0 plus? Think about that. Well, it's going to be 2 amps. And there's two ways you can explain that. Okay. I mean, there's 12 volts there. At t equals 0 plus, there's 12 volts at that point. There has to be 2 amps flowing through that 6 ohm resistor. And that's all your transients. Now you can go through and you can calculate the voltage across the inductor at t equal infinity. Has to be the voltage across the resistor at t equal infinity. They have to be the same thing. You should tell me what that is. What's going to be 0 volts? Why? That looks like a short circuit. Why? The observation we made is in the steady state, when all the short-term transients die out, inductors look like a short circuit. And you could go through calculating the current to the inductor at t equal infinity and the current to the resistor at t equal infinity. And if you look at this problem right here, problem page 10, here's another example where we have a resistor and an inductor. They're in series. And you should be able to figure out the transients, which basically are voltage at t across the resistor at 0 plus, voltage across the inductor at 0 plus, and the current through the inductor at 0 plus has to equal the current to the resistor at 0 plus. That's all 4 possibilities. 1, 2, 3, 4. These have to be the same currents because it's a series circuit. And you should be able to go through and be able to calculate each one of these in the transient. And then do the same thing down here in the steady state when that switch is closed for t equal infinity down here, but it looks like a short circuit. Once all the high frequency... See, let me explain why this is happening. When you first close that switch, that voltage at that point tries to jump up like that. It tries to do that. Okay? Now, there's a lot of high frequency component in that. There's a lot of high frequency component in that edge. And at the higher frequencies, that's when these inductors are characteristic, because in the DC state, they look like a short circuit. The same thing with the capacitor. When you first close that switch, there's high frequency component in that step of that voltage. And that's when the characteristics of the capacitors and inductors show themselves. In the steady state, that capacitor is going to look like an open circuit. And that inductor is going to look like a short circuit. So you should be able to go through each one of these problems. Example 1, example 2, example 3, and example 4. Shouldn't have any problem with that. And then on page number 11, we already looked in your book at example 6.5 and 6.6. They work out examples 6.7 and 6.8. You should just look them over. In summary, what we've covered so far, and these are equations you should have written down somewhere when you take your quiz or you take the exam. charge is equal to C, the capacitance, times the voltage in coulombs. We talked about that equation. For capacitors, the current to a capacitor is C dV dt. And the voltage to the inductor is L di dt. And then you can get the corresponding parameter for capacitors. If the current is a derivative, the voltage is going to be the integral. And for the inductor, if the voltage is a derivative, the current's going to be the integral. What I did when I memorized this is the one I memorized. For some reason, I always, it had a ring to it, L di dt, L di dt. So I memorized the voltage across the inductor with respect to time is equal to L di dt, the current through the inductor, the derivative of the current through the inductor. And I know conversely that the current to a capacitor was C dV dt. So I memorized this one, I could get this one, and then be gone from here to here and here to here was simply the opposite parameter in the integral of the opposite parameter up here. However you memorize these, I don't care, but you have to memorize these. I'm going to give you a quiz for certain sometime within the next week. Could be next time I see you. I do this every semester for 30 years. You're going to get a quiz, and you're going to have to write these down from memory. And you're going to have to know from memory on that quiz not only how to write those down, but you're going to have to know that voltage cannot change instantaneously across the capacitor, and current cannot change instantaneously through an inductor. You're going to have to know those 6 concepts in this quiz, so get them memorized as quickly as possible. You're going to use them many more times. And that concludes this lecture.